Hello, my name is Nelson Stoffer, and I'm a computational ecologist at the USDA ARS Jornada Experimental Range, and I'll be talking about how to implement an AIM sampling design for data collection during a field season. The intent is that by the end of this presentation, you'll be comfortable with the basics of sampling, how and when to reject plots instead of sample them, how to plan a hitch, that is, a trip to sample one or more points, and how all of these things work with revisit sampling designs. Ideally, we would complete an inventory or census in which we measure absolutely everywhere. In our case, that's not possible because we're dealing with millions and millions of acres of land. So instead, we sample the landscape, which means that we collect data at various locations, our sample, and use those to estimate the properties of the landscape on the whole, our population. One example of sampling that you may be familiar with is political polling. If pollsters want to know the political beliefs of a population, for example, Gen Z, there are too many people in that population to ask every single person what their political perspective is. So instead, the pollsters ask a subset, the sample, of the population about their beliefs, and then extrapolate from those answers to make estimates of the whole population that the sample was drawn from. This is why political polls report the number of respondents and the methods that they use to contact them. They need to be upfront about how a sample was selected because that sample may be biased and non-representative of the whole. For example, we should suspect bias in a polling effort that only used landlines to try to contact Gen Z because, based on our knowledge of the communication habits of Gen Z, we'd expect that the respondents are non-representative of that population. In order to responsibly sample an area in a statistically valid way, we need to reduce or eliminate any bias in the sampling effort. Minimizing bias happens at the creation of the sampling design and sample selection, but also is an ongoing part of implementing the design, which is where you come in. A population is the larger group, or in our case, area on a landscape that we want to describe. We draw the samples, our plot locations, from the population, also called our sample frame, in order to gather the data that can be used to describe the population. There are restrictions on extrapolating from our sample, though. Data from a sample can only be used to describe the population that it came from. So if your sample frame didn't cover an area, and therefore the area didn't have a chance to be included in the sample, the data can't speak to that area. Areas that are covered by a sample frame are within what we call the inference area, because we can infer conclusions about them from the data. In AIM, our sample frames are almost always restricted to BLM land, because that's where the BLM has the authority to collect data and manage the landscape. So it's the area that we need to know about. The extent depends on the project though. For example, a sampling design trying to answer questions about a field office's land use plan, which covers the whole office, would use all BLM land within the field office as its sample frame. Likewise, an effort focused on sage-grouse would probably use a sample frame restricted to sage-grouse habitat. In that case, the data collected would be only applicable to the sage-grouse habitat and not to any areas outside of it, because the inference area is limited to the extent of the sample frame. Bias has come up a few times, but we haven't precisely defined it yet. Bias is the difference between the estimated value and the true value, or aspects of sampling that make the sample non-representative of the population. This is inevitable with sampling, but can be controlled if we do our best to make sure that the sample is representative of the whole. In this diagram, the true value is represented by the orange dot in the middle of the target. Our goal is to get the farthest right result, where we are both accurate, hitting the bullseye, and precise, our values agreeing well with each other and having low variance. Lower variance means more confidence in your estimate, but in situations where sampling is biased, we can end up confident in an incorrect value, as in the second from the right. Variance, that spread of values, is largely controlled by how many plots you sample and aspects of the sampling design which have been determined earlier in the design process. What you have more control over is bias introduced through non-representative sampling resulting from how the sampling design is implemented. You won't be making decisions about how to draw sampling designs, but you will be making decisions about how to implement them. These are the general steps for implementing a sampling design for an AIM project. First, you'll take a look at your plots in the office and apply the project's rejection criteria. This may have already been done for you by a project lead when you start the field season. The next step will be to plan your sample efforts, or your hitches, for the remaining points. A hitch, generally speaking, is the group of plots that you'll collect in one period of data collection, including the order in which you will sample the plots in that area. There's then a second round of potential plot rejection. Regardless of what happens at a plot, if you collect data or reject it, we need to know what the fate of that plot was, what happened at that plot. If it's rejected, you need to track that it was and why. If it was sampled, you need to track that, as well as when and exactly where the data were collected. And if it wasn't evaluated one way or the other, then we need to know that also. The first step in implementing a design is office rejection. Let's talk about plot rejection in general. We have lists of criteria that you apply in the office and in the field at a sampling location to determine if it should be rejected. These criteria are things that either make sampling a plot challenging or unsafe. That said, there is some room for a project lead to decide which rejection criteria to apply to their particular project. However, rejection criteria need to be determined before field visits ever take place in order to reduce bias. Otherwise, by changing criteria mid-season, you could skew sampling by collecting data in places you would otherwise have rejected if you'd only been there earlier in the season, and vice versa. In order to complete office rejection, you're going to plot your field sites along with ancillary data that will allow you to determine if you can or should office reject a plot. These are the standard office rejection criteria. These can all be checked using data sources like a roads layer in GIS, topographic maps, and land ownership information. Several of them have to do with safety, like the 3-mile walking distance or slope greater than 50%. The others have to do with points that are inaccessible or unsuitable for sampling. With regard to rejection based on distance from roads, make sure that you have an accurate road layer and confer with folks in your office to make sure that you aren't rejecting points because of distance that could be accessible via a road that is missing from the map. Office rejection should rely on local expertise. Odds are there's someone in your office who knows the land pretty well and can help you determine if a plot is actually inaccessible. Office rejection for slope is tricky. Often a digital elevation model, or DEM, is used to measure the slope, but they are fairly imprecise. So a plot that you may be able to safely sample, especially if you implement the moving criteria that we'll discuss in a little bit, could end up being rejected based on the DEM. Plots should be rejected for slope in the office only if it's obvious that they can't be sampled. For example, there are clearly very steep cliffs with no adjacent gentler slopes. Rejections due to non-BLM land will be rare, but not impossible. For those of you sampling older designs, there may have been changes in ownership since the design was originally drawn, but that should be the only scenario in which this rejection criterion is applicable. Just keep this in mind and make sure to use the most recent local land ownership layers from your office. All of these rejections should be tracked through the web map, accessed through ArcGIS Online, or through the mobile app Field Maps. This process is covered in a separate presentation on data management. Hitch planning is the most creative you'll probably get while implementing a terrestrial aim sampling design. There are some rules to follow, but it also requires forethought and strategizing and should be revisited often. You can't plan an entire season's worth of hitches at the beginning because there will always be complications to adapt to. One of the most important aspects of hitch planning is maintaining the order of plots. Your plot IDs should all end in a number, indicating the order in which they should be visited. The goal is to end the season without any holes in your sampling order, except those caused by rejections. This means that there's some flexibility to sample slightly out of order during the season, so long as points are skipped over only temporarily. For example, points 1 and 3 may be very close together, while 2 is on the other side of the field office. It would be acceptable to plan one hitch that hits 1 and 3, and then a second hitch following that, which includes 2. But it is important that 2 is sampled before the end of the season. Holes in the sampling design cause spatial bias to be introduced and can result in an unrepresentative sample. There are 2 complicating factors that you might have in your design. The first is strata. If your design is stratified, then each point belongs to a stratum. In the case of a stratified design, you need to sample points in ascending order within each stratum, making sure that you're sampling each stratum. So, the first hitch of the season should sample the lowest numbered plots in the strata that you're visiting. For example, if you have shrubland and grassland points, your first hitch might be to sample shrubland 1 and 2, the first 2 points in that stratum, and grassland 24, the first point in the grassland stratum. At any given point in the season, the points that you've sampled so far should be spread across the strata proportionally. That is, if 20% of your points for the season are in shrubland, then at any given moment, approximately 20% of the points that you've sampled so far should be from shrubland. This means that even if the season is cut short, we can still avoid introducing bias by sampling a strata more heavily than intended. The other complication is revisit versus non-revisit points. Some designs have points that are revisited at regular intervals, and then other points that are intended to be visited just once. In these cases, you'd treat the revisit and non-revisit the same way you would strata, sampling them in ascending order within the type, trying to keep the sampling proportional between the types. The difference is that you should prioritize completing the revisit points because it is important that they be sampled in the correct year. I know that's a lot, but there are several examples coming that should help make things clear. These are examples of ways you could introduce bias, systemic or random, into your data with the way that you implement your sampling design. If you start your design by ignoring point order and visiting the plots that are most convenient, the potential exists that you would never get to the more inaccessible plots. This introduces bias toward those convenient plots. The plots that are most accessible to you are also most accessible to everyone else. So these plots could also be more affected by anthropogenic impacts and may not give you a true representation of the landscape. If you start on one side of your field office and work to the other side, you could end up missing whole chunks of your project area if you run out of time in your field season. This obviously would introduce spatial bias. What if there's an invasive species that only occurs in one portion of your project area? If you miss it by not visiting that area, or overrepresent it by only visiting that area, your data would be non-representative of the project on the whole. The points are numbered such that as long as you go in order, the points sampled will be spatially balanced with each other. Even sampling out of order can introduce spatial bias that you might not be aware of. Once you've gotten through the initial steps of HITCH planning and you've made it out to your sampling locations, you need to deal with field rejection. As mentioned before, there are some of the rejection criteria that you just can't reliably apply until you get into the field. For example, there are plenty of ways for a plot to turn out to be unsafe to sample, ranging from a herd of wild horses to an aggressive human. If, based on checking the office, you thought that your plot fell on an area of less than 50% slope, but you get there and you can't actually get to the spot because everything around it is extremely steep cliffs, then you would reject it based on slope or safety. Once again, all of this information should be documented in the web map or through field maps. Sometimes you can encounter a reason to reject, like your plot crossing a road, that could be solved if you just move the plot a little ways. For that reason, we have a movement protocol. By the time you hike all the way out to a plot, odds are that you aren't going to want to reject it, especially for something like a rattlesnake in the middle of it or because it crosses a road. In these kinds of situations, the best option will probably be to implement the moving procedure. The basic gist is that you can move the center of the plot 50 meters in the cardinal directions until you find an area that you can sample. You start by trying to move north. Then, if that doesn't work, you try east, then south, then west, before concluding that you should actually reject the plot. We do this systematically and following set rules so that we don't end up just picking where to sample, which would potentially introduce bias. There is a place in the plot tracking to note that you moved the plot. Also, this is something to keep in mind during office rejection. Several of the rejection criteria can be softened because you'll be able to implement the moving protocol. If you've made it all the way through the movement protocol and still can't sample, then you can reject the plot. When you reject a plot, we need to replace it. To do that, we just add the next highest ordered point in the design to the end of our seasonal sampling plan. In field maps, the points to use to do this with should have the status oversample, which just means that they're available as replacements for rejected base points. So, for example, if you plan to sample the first 10 points, BFO1 through BFO10, but have to reject BFO3, you would add BFO11 to the end of our sampling. Note that you would not immediately sample BFO11. You'd still sample in ascending point order. Also note that if you have a stratified design, you do this on a per stratum basis. So if you reject a grassland point, you'd add the next highest ordered grassland point to the end of the sampling plan. Same goes for revisit and non-revisit points. You replace them with the next of the same kind of point. Remember that our spatial balance is preserved by going through the points in order. So don't immediately sample the replacement point. Wait for it to come up in the sampling order. We'll work through an example in the next few slides. Note that these are stratified examples because those are more complicated, but the principles are the same for all designs. Before any sampling has happened, all the points have the status not eval, meaning that they're not yet evaluated, so they haven't been sampled or rejected yet. You can see here that the design has two strata. Sage Steppe has 4 points to sample, SS1 through SS4, and Salt Desert has 6 points to sample, SD10 through SD15. As the field season moves along, the points are evaluated. Some of the points are evaluated and rejected instead of sampled. In this case, as the crew worked their way through the points, they had a few complications. Before the field season even started, the crew rejected SD11 because they would need to pass through private land to access it, and the landowner has declined to let them. Then, when sampling SD12, they needed to use the movement protocol. They noted the move when sampling the plot. Finally, when they tried to get to SS4, they were unable to because the slope was greater than 50%. That means that they now need 2 points to make up for the rejections, one in Salt Desert to replace SD11, and one in Sage Steppe to replace SS4. To make up for the rejections, the crew added the next unevaluated points to their sampling plan, which is why the map now shows the points SS5 and SD16. The numbers on the points show the correct sampling order. So in the case of Sage Steppe, that's SS1, SS2, SS3, SS4, which was rejected, and then SS5, which was added to make up for that rejection. For Salt Desert, the order is SD10, SD11, which wasn't rejected, SD12, SD13, SD14, SD15, and finally SD16, which was added to make up for the rejection. In both cases, the new points are only sampled once all the lower number of points in the stratum are sampled. Hitch blending really comes down to two things, so we'll state them one more time. First, make sure that you're sampling proportionally according to stratum if you have a stratified design. If your design is 50% shrubland points, then at any given point in the season, 50% of the locations you've sampled so far should be from the shrubland stratum. Likewise, if you have 80% revisit and 20% non-revisit, you should sample those categories in those proportions. Second, try to not leave gaps in the numeric order of points. It's okay to have a gap because points were rejected, but it's not okay if there's a gap because points were left unevaluated. In order to be efficient about your hitches, you can leave small gaps in the order temporarily, but in those cases, try to fill the gaps as soon as possible on a subsequent hitch. This is an example of a sampling design with 25 points split between two strata. 40% of the points are in the forest stratum, shown in dark green, and 60% are in the shrubland stratum, shown in light green. This is an example of bad implementation of that design, which we drew from real life. The field crew decided that they would start sampling the plots furthest from the field office so that by the end of the field season, when they were tired, they'd only have nearby plots to worry about, which left gaps in the point order that they planned to fill later. But their field season was cut short, preventing them from filling in the gaps and resulting in pronounced spatial bias in the data. They also ended up with 60% of their sampling effort in the forest stratum instead of 40%, overrepresenting that ecosystem and biasing the data. The moral of the story is that you can't assume you'll have more time. Be careful to always be sampling proportionally and to fill in whatever small gaps you leave as soon as possible. This is a more correct, but still imperfect, implementation of that same design. In this case, the field crew still only got to 15 points, but they sampled proportionally correctly. 60% of the effort went to the shrubland stratum and 40% to the forest stratum. They avoided that potential source of bias. Within the forest stratum, they did a good job of sampling in order, but the shrubland stratum still has some gaps. It's not as obviously spatially biased to the naked eye as it was with the previous implementation, but they should still have worked to avoid gaps in the sampled point order. We've talked a bit about revisit designs, but I want to clarify how they work. Revisit designs have two different kinds of points, revisit and non-revisit. Revisit points are those that will be revisited at regular intervals. In some cases, revisit points will have already been sampled at least once before, but that's not true for all revisit points. Non-revisit points are new points that have never been sampled and are planned to only be visited once. As mentioned before, you need to sample these two types of points proportionally. If 80% of your plots for the season are revisit point locations, try to make sure that 80% of the points you've sampled are revisit points. Don't do something like try to knock out the handful of non-revisit points first before focusing on revisit points. You should receive revisit reports for plots that have been sampled before. These will tell you what to expect and how to get to the plots so that you can sample in the same location. If you are going to a previously sampled plot, you should carry out all of the sampling methods unless directed otherwise. For example, if the previous visit collected adequate soil information, you may not need to dig a soil pit. This concludes the presentation. Hopefully at this point, you have an understanding of the basic concepts of sampling. You understand how office and field rejection work. You understand how HITCH planning plays out, and you're comfortable with the concept of revisit sampling designs.